In this video, I would like to discuss energy and more specifically conservation of energy bar graphs and the importance of understanding this before we proceed into problem solving. As I mentioned earlier, energy is a conserved substance-like quantity with the capability to produce change in physical systems. Energy can be stored in a system in a variety of ways, which we've discussed earlier, such as kinetic energy, which is energy of motion, or gravitational energy, which is the energy stored in a gravitational field of a system, or elastic energy, which is energy stored in a system when it's deformed, or all these other types of energy like dissipated chemical energy, nuclear energy. When energy is transferred between a system and the surroundings, which we call the environment, then work must be done. To help understand energy storage and the transfer of energy, we use an energy conservation bar graph, which is shown over here. So let's take a look at this following situation. We have Buffy over here who's throwing a water balloon over at Biff below at ground level. And we're going to use an energy bar graph to analyze the energy storage and transfer occurring in this scenario. And whenever we look at each situation, we want to kind of follow the following rules. First, we list the objects in the system within a circle. Second, on the physical diagram, we'll choose where we would think zero height will be. For at that particular location, the gravitational potential energy will be zero. Then we sketch an energy bar graph for the initial position, and then we do one for the final position. And if there's any energy flow in or out of the system, we use an arrow in or out of the system. And then finally, we can write a qualitative energy equation for this energies that have been stored and transferred within the system. Okay, so if you look over here, there's our first little bar graph, and this is showing the energy initially. So this is when the water balloon is in Buffy's hand and it's just leaving her hand and about to just leaving and going off at this particular spot. And then over here in this picture is when the water balloon is hitting Biff onto the head. It's still moving, but it's just about to strike Biff's head. Okay, so in this case we've chosen Biff, the Earth, and the balloon to be our system. So Biff, this person here, the balloon, and then the Earth, the ground that Biff's on, to be our system. You'll notice that we did not include Buffy into our system. Buffy is on the outside, so it would be considered part of the environment or surroundings. Since Buffy is not included in our system, then we don't include her in this circle. So on the outside, you can see it's written over here. But you don't even need to write her there if you want. So secondly, now Buffy throws the balloon and applies an external force on the balloon as it leaves her hand. And so in that particular case, there must be some energy that's being transferred into the system. And that's represented with this arrow drawn into the circle. And this represents the work that is done by Buffy on the system, which includes Biff, Earth, and balloon. If you look at our final picture here, we have several different types of energy. Actually, let's go back to the first picture. If you look at it, here we have 1, 2, 3, 4, 5 bars of gravitational potential energy. That's because the balloon is over here at a higher height. So we have some gravitational energy. And we're going to assume down here, and we might indicate that, at this particular location, the height is 0. But at our final position, you'll notice that we still have some gravitational energy. It's 3 bars, but it's less than what we had because we started with 5 bars. That's because the height here is higher than the height here. So we start with 5 bars of gravitational energy, and then we end up with 3 bars of gravitational energy and 2 bars of kinetic energy, and then a little bit of energy that has been dissipated. So this is the dissipated energy. So if you count here carefully, you'll see that we started off with 1, 2, 3, 4, 5, and then at the end we have 1, 2, 3, 4, 5, 6, 7 bars of energy. So suddenly you've got more energy in the final situation than you did at the end. So why is that so? Where did this extra 2 bars of energy come from? Well, if you look carefully over here, Buffy did work on the system. And it's exactly, if you count here, 1, 2 bars. So really, you had some gravitational energy plus the work done. That adds up to a total of 7 bars of energy, and at the end, you have 7 bars of energy. So now we can proceed to writing our conservation of energy statement. So we started off with gravitational energy, and I've listed that as E sub g, but you could rewrite that as U sub g for gravitational energy, plus the work that was done by Buffy must be equal to the kinetic energy, K, plus the gravitational energy, U sub g, plus the extra dissipated energy, E dissipated. And this is our statement of conservation of energy. So what is work then? When is work being done? And we'll look at that more closely in our next video. But basically, work is done when there's some external force that is being acted on the system. It is also equal to, if you look at it carefully, you could consider this is the initial energy, all of this. We'll write that as E initial. And all of this energy, all these added up, is E final. So you could look at it this way. This is really the initial energy, the gravitational energy, plus the work done must be equal to all of the energy at the end. We'll write is E final. So the work is really equal to the final energy minus the initial energy. The work is really equal to the change in energy. And this concept is known as the work-energy theorem. When you do work, there is a transfer of energy between one form of energy to another form of energy. And when work is done on a system, then energy flows into the system. And when work is done in the opposite direction, then energy can flow out of the system. So whenever the energy initially and the energy finally are not equal to each other, then we know that there is a change in energy. And if there's a change in energy, that change in energy is equal to the work that was done on the system.